Okay guys, welcome to this tutorial on how to calculate ratios when it's talking about gears and pulleys and things. We're looking at task 27, and if we have a look at task 27, it consists of a number of pulleys and a number of belts joining those pulleys together. A couple of things to take note of, that we have one large pulley with a diameter of 30, which then connects to a smaller pulley with a diameter of 22, which then also connects to another another pulley the same size as it, also diameter of 22. So we need to go read the question, and the question reads something like this. The pulley system shown requires an exact 180-degree turn in the direction of the arrow. So let's first of all do that. There's the arrow. And so we're turning this actual pulley 180 degrees. So there's a start point. Let's say that's the red point which indicates the start point. And we're going to turn it 180 degrees. If we turn this pulley 180 degrees, where will these red dots on the other two pulleys, where will they end up? Will they end up being in 180 degrees from their start position, or will it be something different? I think I might have just said the rest of the question. Let's have a look. Yep, add 3 green marker dots to the 3 pulleys to show where the pulleys will finish. So it's asking us to work out where these dots here, where they will move to if this pulley moves 180 degrees, or if you like, half a turn. Okay, so I think the easiest way to start this is to draw ourselves a diagram of what's actually happening there. So coming over to a sheet of paper here, and I'm going to draw myself a large pulley. I'll label it, it's 30, and a smaller pulley, let's put the phone there, smaller pulley at 22, and then to another smaller pulley, well, same size pulley as it, also at 22, but ordinary. Get back there, draw the belts going between them, and this one's a larger one to a smaller one. Okay, alright, so a couple of things we need to first of all work out is which pulley is driving and which is the driven. So it said this large pulley here, the one that's 30, was the one that was rotating 180. So we're going to call this one the driver. So if you like, if we use our what do you call it, our pedal analogy, this is the one with our pedals on our push bike, and this pulley here, the first one we're going to consider, so we'll call this pulley A, pulley B and pulley C. The relationship between A and B, is it an increasing ratio, pulley ratio, or is it a decreasing pulley ratio? Let's have a look. If the pedals are on the driver, we have a large pulley on the pedal, a small pulley on the back wheel. We know from our bike analogy that that's going to be an increasing ratio. So we would expect to see pulley B move further around in one revolution than one revolution for pulley A. So let's first of all work that out. Let's work out what the ratio between pulley A and B is going to be. So like we've done for our previous examples, we're going to create a bit of a column. On one side of the column I'm going to put the driven or the output, and on the other column I'm going to put the driver or the input. This is for pulleys A and B, or A to B I suppose, as a ratio. So the driven pulley, the output is B, which is 22 diameter. Now we don't have to work out circumference yet, we might deal with that a little bit later on. And the diameter of the driver with the pedals on it was 30. So let's now reduce this down. So we need to get 22 down to 1. So we divide 22 by 22 gives us 1, which means where we do this side, we have to do that side. So 30 divided by 22, I think I I had it written there before. Yeah, there it is there. That comes in at 1.36. So, going back to our initial sketch, we have an increasing ratio of this first pulley train AB of 1.36. So that means that every time that this pulley here starts in this position and does one revolution, then we increasing the revolution of pulley B. It would go around once and then another 0.36, so it's basically another third. So if we said that was one revolution, that would be a third there, 2/3 there, and back to 2. So we're saying that for one revolution of A, B would do 1 1/3. Now that's handy to know, but if we have a look at the question actually asks us how far or where were these dots on pulley B and C end up after A has spun around half a turn, not one whole turn. So the dot on A was there, the dot on B was there, and the dot on C was there. So 12 o'clock, 6 o'clock, 3 o'clock. So if this dot here, or this mark on the pulley, does 180 degrees, moves to here, then the ratio between A and B, or the increasing ratio for a complete turn, would be 1.36. But we're only going half a turn. So therefore we would expect not one turn, but half a turn. We would have to divide that by 2. So therefore we also need to divide the ratio on the other side by 2. So that would come down to, say, close enough to 0.7. So for 180 degree turn on this pulley, 180 degrees or half a turn, we would expect to see this pulley move 0.7 of a revolution. So from there to there would be 0.5. If we divided this up into thirds, because 0.7 is just a little bit over 2/3. So there's a start point, there's 1/3, there's 2/3, 3/3 would be a revolution. So that would be 1/3, 2/3, so 0.7 would be approximately there. So our dot would move from there around and would finish there for 180 degrees. Okay, so that's solving the positional movement of our dots for A to B. What about from B to C? Well, that's pretty simple, because B and C are exactly the same, so therefore the ratio is going to be 1:1, which means however far this moved around will be the same on C. So if it starts there and we go thirds again, so there's 1/3, 2/3, 3/3, we know it's 0.7, which is just over 2/3. So we go around like so. But there's something I have neglected to check, whoops, and that is, are these pulleys still spinning the same direction? Let's have a look. If that spins clockwise, this one spins clockwise, yes, next bolt spins clockwise, so they're all spinning in a clockwise direction. Okay, so that is approximately where the dots would finish up. We could also work out exact distances by throwing in there some pi times d, but we won't worry about that one for this explanation.